MIT. Let's see, for some reason, my video was turned off. Professor Sze is an associate professor of electrical engineering and computer science at MIT. She is a director of one of the labs in the research lab of electronics there, RLE. She works on computing systems that enable energy efficient machine learning, computer vision, and video compression and processing in a wide range of applications. She is widely recognized for her leading work in these areas and received many awards, including DARPA Young Faculty Award, AFOSR grants, as well as several faculty awards and grants from Google, Facebook, Qualcomm, and so on and so forth. She is a co-author of the book, Efficient Processing of Deep Neural Networks, that she will be mentioning briefly in her talk today. And today she will talk about how to evaluate efficient deep neural network approaches. And after about 40 minutes or so of the talk, Professor Sze will be available to answer your questions. So now I am giving the floor to Professor Sze for her talk. Oops, sorry. Let me go back, because I think I made a mistake of not sharing the screen with you, correct? Now I have to share the screen and hit all the right buttons, which I think would be fine now. And we will go to this screen right away. And before I start, I would like to hear from somebody if you hear me, and complain if you will not be able to hear her voice, okay? So I presume everything is okay now, right?
So we know that, over the recent years, there's been a huge amount of work in deep neural nets. And we've also known that there's a lot of work on trying to make neural networks more efficient. In fact, this whole workshop is about that. So today I wanted to shed some light in terms of what are the things that we should be thinking about when we are looking at these various different approaches. I want to say the material that I'm going to present today is in collaboration with many folks, and that the slides are also available on our group website. And also we have a book that we just released that covers this topic. So if you want to take a deeper look, I would invite you to visit this book. So again, so the focus of my talk today is how we're going to actually evaluate these DNN approaches, the many approaches that people have come up with. There's been many DNN accelerators and approaches over the past few years. It's too cumbersome to cover them all in one talk, but what we're going to focus on is how to actually evaluate these approaches. And this will include both the hardware aspect of DNN accelerators, so specialized hardware for DNN is increasingly popular, as well as efficient algorithms and DNN models as well. So how do you evaluate those and their approaches? And what are the key metrics that we should really be thinking about and that should be measured and compared across these various different approaches and techniques? So to start out with, a common metric that's often reported when it comes to computation is TOPS, or TOPS per watt. So a TOP is basically the number of tera operations per second, and TOPS per watt is, how many of those operations per second can you cram in under a certain amount of power consumption. And you'll often, if you look at, hardware publications or press releases, people often report that. However, what I want to highlight in today's talk is that it doesn't provide sufficient insight on the hardware capabilities and its limitations, especially if these are reported based on peak throughput and performance. And just some, one quick idea is that, one easy way to get very high TOPS per watt is just to use a ring oscillator, and it's going to be the simplest thing. It's just basically an inverter that flips up and down, and that's going to be the most efficient TOPS per watt you can get. But whether or not it does anything meaningful is something else, right? So it's important to consider more metrics than that. And so when it comes to looking at efficient processing of deep neural networks, there's many more metrics than just operations per watt itself. So the first thing, of course, that we care about is accuracy, right? So obviously one of the reasons why this field has taken off is the very impressive state-of-the-art accuracy it's achieving on many important tasks. But there, of course, it's important to factor in, the type of data set that you actually are achieving high accuracy of. So quality of results is very important. Throughput is very important. So often you want to, if you process a lot of data, you want high throughput, so analytics on high volume data. Also, if you want to have real-time performance, for example, video at 30 frames per second, throughput is also going to be important. But when it comes to real-time or interactive applications, latency is going to be very critical. So for example, autonomous navigation, where you have to interact with your environment, there latency is very key. And latency and throughput are actually quite different. We will talk a little bit more about that later on, but latency is very challenging to achieve, but also very important. Then there's also energy and power consumption. So on embedded devices that are battery operated, you're going to have limited amount of energy. And then power consumption is very critical in the data center, because power is also often associated with heat dissipation, and there's a limited amount of ability to cool the hardware in the data center itself. And in fact, some of the power is actually used to run the cooling engine. So power dissipation is really a challenge. Of course, cost is also an issue. Whether or not you're paying a large cost for a large piece of hardware or a small cost is really critical when you're evaluating the solution. We shouldn't evaluate something that's hundreds of thousands of dollars versus something that's hundreds of dollars of cost. Flexibility is really key. So given the amount of research in this space and development in this space, there's been a huge amount of DNN models used for a wide range of tasks. So it's really important to be flexible and support these tasks. And then scalability is really key. So the ideal thing is that when you scale up the amount of resources, your performance will also increase as well. So let's dive a little bit deeper into each of these key design objectives and metrics. So the first thing often people think about is, how do we increase throughput or reduce latency? So often this is associated with reducing the time it takes to process each MAC, or multiply accumulate, which is the key operation in a deep neural network. This can involve things like reducing the critical path of the hardware, which often allows you to then increase the clock frequency. Or if you're looking at programmable hardware, how do you reduce the instruction overhead? You might want to avoid performing unnecessary MAC operations. This can allow you to save cycles, so this will become important when we talk about things like sparsity. You might also want to increase the number of processing elements. So you have more MACs that can operate in parallel. Of course, here what's important to consider is the area cost. So just making things parallel doesn't come for free. In order to increase the number of parallel MACs, you often have to consider the area density, or the area it takes per PE, or the increasing the overall area cost of the system. And then even once you put these processing elements down, it's really important that they're actually being used to do computation. So the PE, what we call the PE utilization, is really key. So we have to keep all the PEs busy. The max you can achieve is the peak performance of 100%. They're all being utilized, but this is often very challenging to achieve. Some strategies that people often do to increase utilization is to distribute the workload to as many PEs as possible, so as many of them get work. We also want to make sure that the workload is balanced, because if we put too much work on one processing element, that's going to be the long pole that's going to limit the throughput. And then, of course, you need to make sure that you have enough memory bandwidth to deliver all the data to the processing elements, so that they're not idle and just waiting for the data to arrive. And then low latency is an additional challenge on top of all of these, which it means it has to have a small batch size. So many of you know that to increase throughput, if you run on larger batch sizes, you can amortize a lot of the data loading costs and you can achieve high throughput. But if you need to batch a lot of data, that means you have to wait for a lot of data to arrive, and that's going to increase your latency. So this is the tension I was kind of hinting about between latency and throughput. So low latency is even more difficult to achieve sometimes than high throughput. One way to evaluate this, or in terms of the performance or throughput of a system, is using this Eyexam framework that we've developed in our group. And this is really a systematic way of understanding the performance limit of any given DNN hardware as a function of the specific characteristics of the DNN model or the network architecture. and the hardware design itself. So it basically has two axes. The vertical axis is the number of MACs per cycle, and the horizontal axis is the MAC per data, so amount of data reuse. And if you want to dig more into this, here's the archive paper reference. So the optimum case is you want to increase the number of MACs per cycle. So the higher up you are on the y-axis, the higher throughput you are. And you know, the maximum throughput you could get is going to be the maximum amount of parallelism. So this really depends on your DNN model, but you know, how many of those MACs can you operate in parallel? That's what limits it. Then the next step is, depending on what kind of data flow your hardware has, you know, for example, which type of data remains stationary, that's going to now reduce the amount of parallelism you can actually achieve by one. The other thing is, of course, the number of processing elements that you actually physically implement, right? And so this is going to be your peak theoretical performance, is the maximum throughput you can have based on the number of PEs, assuming 100% utilization. Some of you might be familiar with this plot. This is basically the roofline model that was developed in 2009. It's widely used in computer architecture. It basically tells you that you know, based on the number of MACs that you can perform for a piece of data, so amount of data reuse, you can think about that. If you can do a lot of operations per piece of data, then you're going to be what we call compute bound, which means your throughput is limited by the number of PEs. Whereas if you need, you can only perform very few MAC operations per piece of data, then you're going to be bandwidth bound, and then, or memory bandwidth bound. And so there's going to be a slope here. Okay, but this again does not provide the full picture, and often, as I mentioned, one problem is people often report just the peak throughput or their, you know, their tops, for example, but there's other limitations that will also drop this down. So one is, for example, the number of active PEs under a fixed PE array size, or the number of active PEs under the array dimension. This is the utilization aspect that we were talking about. And also this depends on the amount of storage as well. So often if you don't have enough storage for your intermediate data, then you know, you can't utilize all your PEs. And so this is really going to push your peak performance down, or your performance way below, you know, could be potentially significantly below your peak performance. So this is one challenge. And this is, we're going to hint towards this later on, but this is, for example, why the number of MACs doesn't necessarily give you an idea of throughput, because the MACs might not all be able to be processed by the processing elements, in terms of, depends on how we map that DNN model onto this array of processing elements. And then, of course, even on the chip itself, between each of the PEs, if you don't have sufficient bandwidth to deliver the data, your performance is going to come further down. Your throughput is going to come further down. So, you know, the big takeaway here is that there's many factors that affect the peak performance. We shouldn't just look at the number of processing elements and say that this is going to be how fast we're going to run. Similarly, we shouldn't look at the number of MACs and say how quickly this is going to run, because there's many factors in terms of how many MACs are actually going to be processed per second or cycle. Another really important thing we mentioned is energy and power consumption. And so, as it turns out, most of the energy and power consumption is not consumed by doing operations like additions and multiplications. Actually, most of the power consumption comes from data movement. So coming from delivering the data to the multiplier and adds. And of course, the further away you go, so for example, SRAM is, you know, from a small memory on chip, would be 5 picojoules, which you can see is already higher than the other operations. But if you go from off chip, from DRAM, much further, you're talking about orders of magnitude increase in power consumption. So one way that you can try and address this from a hardware standpoint is we can exploit data reuse, which means that once I read the data once, or move it from an external, you know, expensive memory once, I try to use it for as many operations at a given point in time. You also could try and reduce the energy per multiply and accumulate. So this could involve, you know, special hardware to reduce the switching activity of the capacitance, or again, reducing instruction overhead. You also want to avoid unnecessary MACs, for example, exploiting sparsity. If you can increase the energy efficiency, then you can, for a fixed, you know, maximum power consumption, which is dictated by the heat dissipation, we can reduce the, or we can increase the number of MACs that operate in parallel. All right, so there are tools that are available out there that allow us to evaluate the efficiency, or evaluate various different DNN processors that are out there, because there's been a huge amount that have been developed over the past few years. And so This is a set of tools that we've developed within our own group, Time Loop and Acceler, just in collaboration with the team at NVIDIA. And what we really need in this space is, given that there's been so many DNN processors that have been developed, we need a way to systematically evaluate and compare all the DNN processors in this design space. And we also like to be able to rapidly explore the design space as well. So once you can compare them, can you also find better network architectures or processors themselves? And as I mentioned, so one tool that we developed within our group is Accelergy. It gives you an early stage energy estimation at the architecture level. And by architecture, I mean you're giving it architecture components like number of processing elements, memory size, and on-chip networks. And then we use Time Loop to map the DNN model onto this architecture. We could also, Accelergy is also flexible enough to support emerging technology. So we know a very exciting area of research currently is looking at, how do we get new devices or new circuits to perform efficient computation. So for example, memristors, have you heard of compute in memory? And so these various different technologies can plug into Accelergy and can be factored into the design of the hardware itself and potentially the design of the algorithm itself. And then as I mentioned, Time Loop is a DNN mapping tool that allows us to basically map the DNN onto the hardware and determine the various action counts, like how many operations, how many max does it do, how many reads or writes does it do. And this whole tool is open source. And really, this is a tool that is used to try and bridge these various different research communities from the algorithms to the architectures and circuits and devices. And it's all open source. So I invite you to visit this website. Of course, any tool is only as valuable as it is accurate. So we validated Accelergy on the Iris processor, and it was able to achieve 90%, 95% accuracy compared to post-layout simulations. It can also capture different levels of granularity in terms of, where does the energy break down between the different components within Iris itself, including a breakdown of the energy per processing element. Another really exciting area of research, as I kind of hinted towards, was, trying to enable processing within the memory storage. If we're talking about data movement being expensive, if you could bring the compute into the memory itself, we could really reduce data movement. And one of the ways of doing this is using analog compute. In particular, what they're trying to do is you can model the memory storage element as a resistor. And then by using Ohm's law, basically, you apply basically a voltage to one side of the resistor, which represents the activation value. The resistance or the conductance of the resistor is representing the weights. Then the natural output of this, based on Ohm's law, is going to be the product of the two, which is going to be the current. And then by KCL or Kirchhoff's current law, you're going to add the currents together, and that's going to be the summation of all these products. So this naturally happens. These devices can be things like non-volatile memory, which is a resistive device. You could also implement them with flash memory or transistors, or using local capacitors. And there's various different ways of doing the accumulation via either current summing or charge sharing. But the main challenge here is that there's going to be increased sensitivity to non-idealities, right? So you're going to be sensitive to small variations. And also, since it's happening in the analog domain, you're going to need conversion between analog and digital and vice versa. And again, so bringing this all together is this whole field of processing in memory. And the whole idea here is that we implement the DNN as a matrix vector multiplication. And the idea is that, you move the compute into the storage that's basically storing the weights of the neural network. So you move the compute into there. And the matrix itself is composed of the store weights, and the input vectors are the input activations. This is what we would call weight stationary flow, because the weights don't move. And so in order to reduce the weight data movement, as I mentioned, we move the compute into the weight itself, so the weights don't have to move to the compute. And then only the output will be the partial sums, or the accumulated value. So there's very few access through the peripheral circuits, or the A to Ds and D to As that are expensive. This allows us to increase the weight bandwidth so that all the weight data can be accessed in parallel. So we basically increase the multiple weights that are accessed parallel, so we can keep all the processing elements busy, so we have high utilization. And of course, because these storage elements are quite small, we can have more max that are operating in parallel for a fixed area, and then also the routing capacitance is also reduced. So that helps us both in terms of energy and speed. And of course, this is just trying to show here that also the Acceler tool that I just talked about, as we kind of hinted towards, can also model these processing and memory types of architectures. And this is just showing and validating on this right-hand side here that you can achieve 95% accuracy and also get a breakdown of the energy across the different layers. Okay, so that's about, energy efficiency and power consumption. Flexibility is also really important. We have a wide range of DNNs that we want to support today, and we could imagine that's going to increase in the future. So we want to reduce the overhead of support. We want to be flexible to support all of these, but we also want to reduce the overhead of flexibility. We know flexibility and overhead, there's often a trade-off between the two. You want to maintain efficiency over a wide range of DNN models, as we hinted towards, because there's increasingly more and more DNN models. These can have different layer shapes, which can impact the amount of required storage and compute, and it can also impact the amount of available data reuse, as we hinted towards. And they might also have these days different precisions across different layers and data types. So you can imagine, weights and activations might have different precision than partial sums at different layers of the neural net, different degrees of sparsity. So if you're going to exploit zeros, the number of zeros and weights and activations can also vary. And then, of course, there's also compute beyond max themselves. So, for example, the activation function. So these are also important things to consider. We also want to factor in, so you want to have hardware that's very flexible. You also want to have hardware that's very scalable. So often we see that it's important to be able to run neural networks or ML on very small devices. So there's this whole field called tiny ML that we're really focusing on, minimizing the energy costs on these tiny little devices. But at the same time, you also want efficiency in the cloud as well. And some of those challenges are very similar. Ideally, you would have one design where you design can scale as you increase the number of resources, like number of Ps, amount of memory, it can scale and cover these various different use cases. Again, so just to kind of give an idea of what are the challenges in terms of flexibility and scalability. So one of the issues is that these days, given that there's so many different techniques to make DNNs efficient, from things like network pruning, so setting weights to zero, coming up with efficient architecture, so decomposing and using smaller filters and reducing precision. There's actually no guarantee from a hardware perspective in terms of which of these algorithms are actually going to be enabled or run on that hardware itself. So we need very efficient DNN processing or hardware. So it kind of demands the DNN processor to be even more flexible given the amount of efficient approaches that have been presented in the past. And just to give you an idea of some of the challenges here. So in existing DNN accelerators, they often rely on certain properties of the DNN model to achieve higher efficiency. So for example, one key approach to achieve efficiency is to reduce memory access. We said data movement is very expensive, so you want to reduce memory access across the PE array. So for example, if you read once, you want to amortize that cost across the array itself. So read one weight and reuse it across the entire array, read one activation, reuse it across the array itself vertically. But the amount of reuse you have depends on the number of channels you might have and the feature map and batch size of the DNN model itself, right? So given these are two kind of configurations down here in terms of how we might exploit the reuse. And we know that these days, given the amount of great research that's happened in efficient network architectures, we might not have the opportunity to be able to exploit reuse in all of these dimensions. For example, if we think of the depth-wise layer, it only has one channel. So in the dimension where we're trying to exploit reuse across number of channels, these types of hardware processors, architectures are going to perform poorly themselves. So we need to kind of really rethink in terms of how we're designing our hardware so that regardless of the DNN model, we can still basically process them efficiently. That might be, having hardware that's efficient enough so that, you might not have reuse in the channel dimension. Can I actually support reuse in some of the other dimensions, right? Or can I have enough bandwidth so that I can still keep my processing elements busy? So can I design a network on chip that has higher throughput bandwidth? And so that was what we explored in the second version of Iris. Really, it focused on balancing efficiency and flexibility. So here we used flexible hierarchical mesh on chip network to efficiently support a wide range of DNN filter shapes, both large and small, different types of layers. So, fully connected, depth-wise, point-wise, convolutional. and also a wide range of sparsity, both dense and sparse. And then shown up here are some of the speedups that we're getting in the second version of Iris on various different layers of MobileNet, which is actually a very diverse DNN model. And it's also very scalable. So again, the idea here is as you increase the number of PEs, do you get an equivalent amount of throughput and efficiency improvement? And it does achieve that. So when we compare it to the first version of Iris, we get an order of magnitude improvement in both speed and energy efficiency. And again, this is having to do with the fact that we've introduced a lot more flexibility in the network architecture itself, or sorry, in the on-chip network itself. All right, so those are, the various considerations, but we should also, for the various different objectives, but we should also dig a little bit deeper in terms of how we want to specify each of these objectives or metrics. So when we talk about accuracy, it should be no surprise to this audience that we shouldn't just take, one number as accuracy and it's fine. It really matters in terms of, what is the accuracy on the difficulty of the data and the task should be considered, right? Is it, 99% on MNIST, or is it 99% on ImageNet, or even something more challenging? And this is because often difficult tasks require more complex DNN models. And so for an apples to apples comparison in terms of whether or not, this approach is efficient, we should really consider, the accuracy or the difficulty of the task when we're evaluating given accuracy. Throughput is also important. So the number of PEs should be reported in addition to utilization, not just assuming peak performance. And so one way to report throughput is in terms of the runtime for running specific DNN models. Latency is also very critical. So as we mentioned, batch size affects latency. The larger the batch size you have, that might allow you to increase high throughput, but it's also going to increase your latency. So reporting batch size is also key. Energy and power. So we should report the power consumption of running specific DNN models, not just the peak efficiency of TOPS per watt. And also we should include off-chip memory access. We saw that DRAM energy is also quite significant, so it's really important to report that. Hardware costs, so how much storage, on-chip storage you're assuming, number of processing elements, chip area, process technology. It's not really fair to compare the performance of a huge chip with a very small chip, or chips of using different transistors or process technology. And then flexibility. Ideally, you'd want to report the performance across a wide range of DNN models. So for example, MLPerf is starting to be a well-known benchmark in terms of giving a variety of models to report on. And even better would be to define the range of DNN models that are efficiently supported. So it's fine to not support all possible DNNs, but it should be clear in terms of what are the limits of the hardware itself. And it's really important to consider have a comprehensive coverage of all these metrics for evaluation, in order to both for people to assess the various different design trade-offs, just to show you where this could go wrong. If a certain metric is omitted, so for example, if someone didn't report accuracy with the specific data set, you could run a really simple DNN on a very easy data set and then claim low power, high throughput, and low cost. However, when the processor might not be able to be usable for a meaningful task when you actually run a meaningful, more complex DNN on it. Another issue is without reporting the on-chip and without reporting the off-chip memory access, one could build a processor with only max and then claim low cost, high throughput, high accuracy, and low chip power. But then when you actually look at the overall system, the off-chip memory access would be substantial and the system power would be substantial as well. So that could be a problem. And then for those of you who work more in the architecture space and the circuit space, there's a big difference between simulated and measured results. Obviously, for measured results where you have to fabricate things, you often build in a certain amount of margin, so that should be considered. So an example evaluation process where we can fold all these metrics together might look as follows. You might start with asking about the accuracy, because that basically determines if it can perform a given task. Then you might ask about the latency and throughput. It can basically tell you if it can run fast enough and in real time. In particular, that might be needed for your particular application. Then you might look at the energy and power consumption, which would primarily dictate the form factor of the device and whether it can where the processing can operate. So is this something that you can have in your pocket, or does it have to happen in the cloud? What is the cost? So basically, how much would you actually want to have to pay for this? And then flexibility. So does it just support this subset of tasks, or does it support a range of tasks? Okay. So that mostly focused on hardware. Another aspect is to focus on the co-design aspects of this. So when we're looking at co-designs, we're trying to make the DNN models more efficient. And the idea here is that by looking, by designing both the models as well as the hardware together, we can achieve what we couldn't achieve with each of these individually. So the first thing you want to consider here is what is the impact on accuracy, right? So when we're talking about impact on accuracy, first you want to consider the quality of the baseline model, right? So is often we say, oh, it degrades accuracy by, this amount, but is the baseline model, already very accurate or not? So how, what is the quality of the baseline model? What is the difficulty of task and the data set again? You should ideally, sweep the curve of accuracy versus latency and energy to see the full trade-off, not just report at one particular data point. Often to support a lot of these co-design things, you need to introduce extra hardware. And this extra hardware, for example, to support variable precision, shapes, or identify sparsity. And so this can actually increase the cost as well. So this additional hardware should not exceed the benefits, and also how adaptive it is. So the granularity of the adaptiveness, for example, the precision, are you able to support every single bit? That's going to increase our hardware overhead as well. So the granularity is something you should consider. And then the evaluation. This is something I really want to enforce. Evaluation, we should avoid only evaluating the impact of these co-design approaches based on the number of weights and max, because they might not be sufficient for evaluating energy consumption and latency. And so again, returning to a slide that kind of summarizes the various popular DNN algorithms, network pruning, efficient network, and reduced precision. Often these focus on reducing number of max and weights. But the real question is, does it translate into energy savings and reduced latency? So if you think back again to what we just discussed, data movement is very critical and expensive. Farther and larger memories consume more power, right? So whether or not you get the data from local specialized, local small memory that's really cheap to access, which would cost you the same amount of energy as doing multiply and accumulate, but we're talking about 1 KB memory, or going off to DRAM, we're talking about orders of magnitude increase in terms of power consumption and energy. It really matters where you're getting the data from. Basically, that's the takeaway here. And so you can't just, for example, look at the number of weights and say that, oh, there's a few weights, so it's going to be efficient. It really, the energy of the weight depends on the memory hierarchy and the data flow. So there's a lot more things to factor in than just the number of weights or number of max. We have in our own group developed an energy estimation tool or evaluation tool where you can put in a DNN model, and based on the shape of that DNN model and the sparsity of the model is going to tell you where the energy actually goes. And as it turns out, it should be no surprise that the number of weights alone is not a good metric for energy. The data types should actually, all data types should actually be considered, not just the weights, but also feature maps and activations. And so then with this information, my recommendation is that we incorporate this, energy or latency information into the algorithms themselves when we're trying to optimize and design efficient deep neural nets, right? So for example, if you care about energy, you should directly target energy and incorporate into the optimization of the DNN to provide greater energy savings. One example of this is this energy aware pruning work that we did back at CVPR 2017. And here the idea here is rather than removing weights based on the magnitude of the weight, it used to be that you remove weights that are small, for example, that could, for example, shown here, half the amount of energy you consume. But if you actually remove the weights that consume the most energy, or based on the energy consumption, you can get a 3.7x reduction in energy consumption. So almost 2x improvement in energy reduction here. Another thing is the relationship between operation, so max versus latency. So we know that a number of max is not approximate latency, for example, here. And so this is actually a plot that's from Google Mobile Vision team, is showing that, on the x-axis you have the number of max, and the y-axis you have the latency. And so for the given same number of max, you have a 2x swing in terms of latency. For the given same number of latency, you can have a 3x swing in terms of max. So you can't just look at the number of max and say, oh, it's going to have low latency. And so together with Google's Mobile Vision team, one way of addressing this is to, again, try and incorporate latency directly into the optimization of the DNN itself. In this particular work called NetAdapt, what we're trying to do is automatically adapt a pre-trained DNN for a given platform. So it's what we call platform-aware adaptation. We use empirical measurements from the platform of latency and energy to guide the optimization itself. The reason why we do empirical measurements is that you often don't have a lot of the detailed information about the underlying platform architecture or the tool chain itself. And another benefit of this particular NetAdapt work is it requires very few hyperparameters to tune. And so that aids with ease of use, which I'll talk a little bit about next. But in general, NetAdapt is available on its project website. Just to give you an idea of what it basically does is it starts off with an initial network that has certain latency and an accuracy that you want, but it has a budget. It wants to reduce the latency by, let's say, 80 milliseconds. And so what it does is that it's going to reduce the number of channels for each of the different layers for one layer at a time. It generates until it hits the actual 80 millisecond budget. Then you measure its accuracy. And then you pick the one with the highest accuracy, and that becomes the input to the next iteration. And then you shrink the budget every single time. And so here, the very few hyperparameters refers to the fact that, for example, the only additional hyperparameter you really need to set is how much you want to shrink by per iteration itself. So this is a very simple form of NAS, but the key message, though, I'm trying to emphasize is that you want to use empirical measurements to drive the decision making here as opposed to a number of ops. And by doing this, by using empirical measurements, you get a much better trade-off compared to other approaches. So shown here is NetAdapt in red. So this is the accuracy versus latency trade-off. Again, here we're showing a complete sweep or trade-off curve. I want to emphasize this. And this is on the smallest mobile net. You can see that you achieve up to 1.7x speed up by taking latency measurements into the design of the neural network as opposed to ops compared to previous approaches. Another thing I just want to emphasize is, often these experiments are shown on image classification, but there are other applications. Speaking of challenging tasks, there's other applications that are also could be valuable and also more challenging. So one example is monocular depth estimation. So given an RGB image, can we assign depth measurements to each of the pixels? This is useful in a wide range of applications, but you could imagine, from robotics to AR, and you can imagine this is going to be more challenging than classification because now your output is dense, right? So you need values for every single output value as opposed to just summarizing in terms of, one class label itself. Now you need an array of outputs. So it's going to be harder to, reduce in terms of complexities and size. And so we want to see if the approaches that we just talked about, like NetAdapt, still apply to this. And this, shows an example of in this case, yes, it does indeed work. So for the same accuracy, and here we're measuring delta 1, which is the percentage of pixels which are within 25% of the right accuracy, we can get a 10x over an order of magnitude speed up using NetAdapt along with compact network design and depth-wise decomposition. This work was presented at ICRA last year, and we actually also got it to run on an iPhone at 40 frames per second, and you can take real data at ICRA in real time to show that it actually works. And all the code and stuff for this astDepth is available at the website. But anyways, the key thing is I just wanted to show that it's important to evaluate on more tasks than just image classification, in the sense that, as we mentioned, the task also really matters when we're talking about co-design of algorithms. One other thing to mention is, okay, so we talked about processing in memory early on. Again, the challenges there is non-idealities and the analog compute and lower bit widths. Right, and the law is also, ADC, so the moving between analog and digital compute is going to be a challenge, and array utilization as well. So often, because moving data from analog to digital analog is very expensive, often it's desirable for processing in memory to have these huge arrays so you can amortize the cost. So again, this has great promise in terms of trying to reduce data movement and being, achieving higher performance. But the thing that I'd like to think about in terms of co-design is also important to think about how we design DNNs for these types of processors. So usually, DNNs are designed for digital processors like GPUs. But when you start thinking about how to design DNNs for processing memory, it could also lead you to different conclusions. So for example, because the devices are noisy, you might need to design DNNs with higher robustness. And we've seen in the past, shown here on the right-hand side, that, DNNs that achieve the highest accuracy might not achieve the highest accuracy when you start adding noise to the system. So the rank order of these are different as we increase the amount of noise. And then furthermore, there's this trend of, making more efficient networks with fewer weights. But in processing and memory, we're trying to reduce the amount of, the cost of weights is very cheap. It's weight stationary because we're basically bringing the compute to the weight itself. And also they tend to have very large arrays, as I mentioned, to amortize the cost. And so if you make the number of weights fewer, you're going to reduce the utilization and basically reduce the benefits of processing in memory. So, the key takeaway here is maybe we want to rethink how we design DNN specifically for processing in memory, and this goes against the existing trend of deeper and smaller filters. Other things to just think about when we're thinking about different co-design approaches, it's important to, consider the the difficulty of using or tuning the algorithms, so the number of hyperparameters. Is the relationship between the hyperparameters and performance clear? If there's uncertainty, it's going to be more difficult to tune. Other aspects that affect accuracy, latency, and energy. So, what is the data augmentation pre-processing? What are the optimization algorithms, hyperparameters, learning rate, schedules, batch size, training and fine-tuning times? All of these things should be factored in when comparing the various different approaches. And then does the approach, how does the approach on different platforms, right? Is it a general method or is it very specific to a given piece of hardware itself? So to summarize, the number of weights and max are not sufficient for evaluating energy consumption and latency. That's a big takeaway. You should directly target the metrics like energy and latency to incorporate them in your design. Many existing DNN processors rely on certain properties of the DNN, which can't be guaranteed. So we need to introduce more flexibility into the hardware itself. And again, we need to think of a comprehensive set of metrics and benchmarks, not one particular, not just focus on, operations per watt or number of max and number of weights. This work is done by, various students, and we want to thank various their sponsors. If you want to check updates on our research, I invite you to follow us on the Twitter feed. Again, additional resources here. So if you want to take a deep dive into this, I invite you to go take a look at our proceedings papers, which is about 30 pages, and also some slides on our DNN tutorial website. As I mentioned, we also have a book that's just coming out this week on this topic, so I invite you to go take a look. It does a deep treatment across the entire stack, from architectures, circuits, to all the way down to algorithms as well. We can have a whole section on the co-design aspect. And some of the chapters are available already on our DNN website, so certain excerpts, so I would invite you to check that out. We also teach a class at MIT, which will actually be held virtual this year, so if those of you are interested in spending 2 days to learn more about this topic, I invite you to check out the course. And then, of course, all these talks are available on our group website and YouTube channel. Thank you very much.
Thank you very much, Professor Sze. Let me stop sharing. I see your face